Waalaikumsalam. Assalamualaikum, madam.
Waalaikumsalam. Okay, Prof. Bekzodjon is here.
Yes, assalamu alaikum.
Okay, Waalaikumsalam. How about your connection over there? Is it okay? Clear?
Yes, for me it's clear. Yes.
Okay, my connection quite poor, so I have to shut down my video. But we still can proceed the webinar, right?
Yes, yes.
Okay. So Assalamualaikum to everybody again. So today's webinar is our second webinar. The title that we're going to look today is using fractional derivative in mathematical modeling. That will be presented by Associate Professor Dr. Bekzodjon from Samarkand University, Uzbekistan. So our session for webinar today is about 1 hour, maybe less than that. So without further delay, I would like to invite Prof to present the topic.
Okay, thank you. Assalamu alaikum, dear colleagues. I hope you are all staying safe and healthy. I'm very happy to continue our webinars on mathematical modeling. Our today's title is Using Fractional Derivatives in Mathematical Modeling. First of all, I want to speak about what is a fractional calculus. All of us are familiar with normal derivatives and integrals like this one or this one. We have first order, second order derivatives, or first integral, double integral of a function. Now, we wish to have a half order, piece order, or another complex order derivatives of a function. So, fractional calculus is derivatives and integrals of arbitrary, real, or complex order. When the fractional calculus appeared, it is appeared with the normal integer order calculus. The first time in a letter corresponding, L'Hopital asked to Leibniz, what if the order of derivative is one half? to which Leibniz replied in a prophetical way. Thus, it follows that will be equal to this one, an apparent paradox, from which one day useful consequence will be drawn. This letter of Leibniz was dated 30th of September in 1695. So this day maybe can be seen that birthday of fractional calculus. We know the calculation of integer order derivatives. Now, how we can calculate the fractional derivatives? There are many formulas, more than 15 formulas to calculate the fractional derivatives. We give some most used ones. The first is Riemann-Liouville formula, which is defined in this form. Another one is in definition of Grunwald-Litnikov formula is defined in this form, and most of used in mathematical modeling or most used in fluid mechanics is Caputo's formula, which is defined in this form. Also, we use fractional time derivatives determined by Caputo in this form. The first problem which is used in which used fractional calculus is tautochrone problem. It was analyzed by Niels Abel. The tautochrone problem asks one to construct a curve with the property that when a bead slides down the curve, the time it takes to reach the bottom of curve is independent from the initial height. It means the initial height, with all initial heights, the ball the bead will reach bottom in same time. Abel used basic physical reasoning to arrive at the following integral equation, which relates the time to reach the bottom of the curve to initial height ty0 in this form, where S is the arc length parameterization of curve that solves the problem. We need to solve this equation for E is dy. We could solve this problem using convolutions and Laplace transforms as Abel did. Alternatively, we could shortcut all of that and recognize that the expression on right hand side can be divided by g 1/2 equals to square root of p. To turn it into a semi-integral, divide each side of this equation by square root of p and move the square root of 2g to the left to obtain and let ty0 equals to t0, since the fall time is constant with the respective to the initial height, this one. We know how to cancel the semi-integral operator. Just take the semi-derivatives of each side of this equation, and the problem is immediately solved by this form. The curve described by this equation is called tautochrone curve. This problem illustrates the main use case of fractional calculus as things currently stand. Normally, what happens is that when analyzing a system, we coincidentally encounter in mathematical statement that happens to be a fractional operator, and therefore we know that we can apply the rules of fractional operators to that systems. Some other applications which the theory of fractional derivatives has been successfully applied are signal processing, tensile strength analysis of distorted materials, electrical circuits with fractals, viscoelasticity, fractional order multiples in electromagnetism, electrochemistry, and tracer fluid flow modeling, neurons in biology, fluid flow in fractured porous media. We also analyze the fractional calculus. We also analyze the relevance with fractional calculus and fractals. The powerful of the fractional operators relies on their non-local power law structure that makes them suitable in describing the memory and hereditary properties of many physical phenomena and processes, and in particular in modeling the anomalous dynamics of complex systems, where scaling power laws emerge as a consequence of such complexity. It has been shown, in fact, that fractional differential equations naturally arise once system characterized by power law long-range interaction or by power law memory. Despite that, their widely recognized usefulness in describing nature, never a clear and universally accepted geometrical interpretation has been pointed out for such operators. So, the development of the theory of fractals, formulated by Mandelbrot in the second half of the 19th century, who consolidated the work of many other prior mathematicians and scientists in general, opened a new perspective to this aim. Since then, several attempts have been made in order to elucidate a connection between the fractional operators and this new geometry, whose anomalous non-integer dimension seemed to be the key of the story. The concept of fractals has been one among these attempts. By fractals, it is usually referred in literature a mechanical model in which classical elements such as springs and dashpot, in this case of viscoelasticity, are disposed as a fractal tree with an opportune power law of scaling postulated for the relevant physical properties in order to obtain a constitutive law of non-integer order for the whole system. So, what is the fractal? In mathematics, mathematician, fractal is a mathematical object that is both self-similar and chaotic. Self-similar means that as you magnify, you see the object over and over again in its parts. Chaotic means that fractals are infinitely complex. Amazingly, these beautiful objects of breathtaking complexity are generated by relatively simple mathematical processes. The first fractals were discovered by a French mathematician named Gaston Julia, who discovered them decades before advent of computer graphics. Julia's works was rediscovered by Benoit Mandelbrot. The famous of all fractals is the Mandelbrot set. The Mandelbrot set is the set of complex numbers C for which function f c z equals to square z plus c does not diverge when integrated from z equals to 0. As you can see, zooming into the Mandelbrot set, it is very self-similar. So, and we can continue to zoom in as we magnify the object. We see the same things over and over again. This is the self-similarity. These two pictures are interesting because they show the same portion of the Mandelbrot set colored differently. The choice of color scheme really influences what we see in the picture. you can answer, is it mathematics or art? Why we study fractals, or where the fractals can be found. Fractals can be found in nature, geometry, algebra, lines, neurons, and others. Some examples for simple fractals are biome trees, Sierpinski triangles, Sierpinski carpet, Koch, snowflakes, and others. In fluid dynamics, fractured porous media also can be described as a fractal networks. In this slide, you can see many types of fractured porous media, which is described by fractals. We know diffusion. In normal diffusion or Fickian diffusion, flow of particles from high concentration to low concentration. Concentration is given by Gaussian distribution. Asymptotically, mean squared displacement is a linear function of time in this form. Diffusion equation is in normal case described in this form. But some processes are an exception to this. Example of these are photocopy machines and laser printers. Movement of holes and electrons in the semiconductors inside them is not the normal Gaussian diffusion. It is an anomalous diffusion. Asymptotical mean square displacement is not a linear function of time. It is function in this form. If here alpha is greater than 1, then we can super diffusion, and alpha is smaller than 1, it is a subdiffusion. Subdiffusion means slow movement of particles, and fast diffusion, super diffusion means fast movement of particles. In fractional diffusion, equation is model is in this form. Here, alpha is not integer number. Examples of some subdiffusion and super diffusions. For subdiffusions, we can example transport of holes and electronics inside the semiconductors, movement of contaminants in groundwater, spread of pollutants from environmental accidents, diffusion of proteins across cell members. For example, for superdiffusion are motion of large molecules and metals clusters across crystalline surfaces, flight of seabirds, movement of spider monkeys, spread of pollutants in the sea, movement of particles inside the rapidly rotating annual tanks. Studies of anomalous solute transport in recent years has greatly increased. This is primarily dictated by the relevance of the problem with application in various industries in technology. On the other hand, there are many unsolved theoretical problems, in particular the question of influence of anomalous nature of the solute transport on the question of influence of anomalous nature of the solute transport on the hydrodynamics parameters is not fully clarified. Conceptually, models can be divided into two large groups. In the first group of models, the process is described from a microscopic point of view. the solute transport is concentrated in a certain single pore or channel with a specific geometry or in a hollow environment between aggregates of certain type. The transfer from the macropores to the environment is described by diffusion type equations. In the second group of models, the specific geometry of the macropores and its environment is not considered explicitly, but instead channels of various size and surrounding rocks are considered as a whole and examined from macroscopic point of view. In this webinar, we will tell you about a problem of anomalous solute transport in a cylindrical two-zone media, in which media consists of two semi-infinitive coaxial cylinders. The inside one, this one is have greater diffusion properties. This is omega 1 zone, and external one with relatively low properties, meaning the diffusion properties in omega 2 zone is lower than in omega 1 zone. So in the omega 1 zone, the solute transport is described by following the differential equation with fractional derivatives. Here Cm is average concentration and Dm is diffusion. In omega 1 zone, Vm is velocity in omega 1 zone. Theta m and theta im is are porosities in omega 1 and omega 2 zones respectively. Beta is derivative order here, beta is. So for second zone, we use equation determined for second zone, we use average solute concentration, CIM, and which determined in the form, which is where Ca is local concentration. Solute transport in the omega 2 zone is described by following diffusion equation, by equation 3. Equation 3 is supplemented by the condition of continuity of concentration at the common boundary of micro and macropores. In a cylindrical covering media, the longitudinal distribution of the solute is not considered, and the external boundary R equals to B is not considered. So equation 5 is used. At the point x equal to 0 over the entire cross-sectional zone, beginning from t greater than 0, in homogeneous fluid enters the medium with a constant concentration of substance C0 and average constant velocity Vm. Initial and boundary conditions for this problem is in the form 6 to 10. To solve this problem, we use a finite difference method. In both zones, we introduced uniform grids in this form, and equation 1 and equation 11 are approximated in the form 12 and 13. Here we use to describe the to describe the fractional derivatives, we use Caputo formula. Here, all functions use it in the great function form, and all initial and boundary conditions are also approximated in this form. To do some computer experiments, we use MATLAB program by the algorithm described before. We find some concentrations in these figures, concentration profiles of CM. It means that in omega 1 zone, and CIM in omega 2 zone. If we here with one, we describe that beta 1 and beta both are equal to 1, and in second one we use that beta equals to 0.8. The calculations results show that a decrease in the order of the derivatives from 2 in the diffusion transport equations led to more diffuse concentration field distributions. So you can say that in second the concentration is distributed more and more in this form also. So here is surfaces of CA. A1 is for the normal case. B1 is when the derivative equals to 0.8, and V1 is when beta 1 is equals to 0.8. You can say that if beta is smaller than 1, the concentration is distributed more than in this one. So we can conclude the anomaly significantly affects the transport characteristics. In this case, the anomaly in one zone is reflected in the transfer characteristics of the other zone. The anomalous effects on the mass transfer between the zones, between macro and micropores. It is shown that a decrease in the order of the beta derivative of 2 in the convective term of the transport equation leads to a more diffuse distribution of concentration field Cm in the macropore. Thank you for attention.
Thank you, Prof. Bekzodjon, for the presentation. I open to a question from the audience, from the participants here. If you have any question to ask to Prof. Bekzodjon. Let me start with the first question if there's no question from the other participant. This is not my field, fractional derivative, but then I just want to know what is the advantage of fractional calculus as compared to normal calculus that we already know, and we always look into the calculus subtopic in the calculus to do the mathematical modeling. But when it's come to fractional calculus, then everybody use the fractional calculus. So what is the advantage of this fractional?
Okay. We all use normal calculus, or why we use fractional calculus. In some cases, the fundamental laws which we use, to describe the process is not useful in some cases. For example, in our fluid mechanics, for porous media, we have Darcy's law, or we have Fickian law, which describes diffusion. But they are usable in porous media, for porous media. But we have some places which is not porous only, which is fractured porous media, or the structure is like a fractal, or like self-similar. Not only porous media, it is fractured porous media. In this case, we cannot describe the process by normal derivatives. So we should use fractional derivatives. It is first. The second one is the most powerful side of fractional operations is they are describing the memory properties of physical phenomena. It means that it is not the fractional derivatives describes not only local processes, but can describe the processes which is over, or can describe the processes with memory.
Okay, so I have the some knowledge on this fractional derivative. It means that it can be used to the situation with condition that the situation is something related to fractal, then we can use fractional derivative. But if situation is not fractal, we can use normal calculus.
Of course.
But it also fractional derivative can also use for non-local behavior, not just only local behavior, right?
Yes.
See. Thank you, Prof. Bekzodjon. Now, is there any other question from the participant?
Hello, yeah.
Yes.
Okay, I'm Suzila from University Malaysia Sabah. I would like to know whether we can implement this theory in image processing, since I saw there's application of this in signal processing. Thank you.
Thank you. I heard that some cases they are using for signal processing, but I am not expert in this field. My field is only mathematical modeling of fluid mechanics. So, but I read some papers that they are using for this one also, for machine learning also using signal processing, also using this kind of mathematical modeling rules. But how they are using, I don't know really.
Yes, I see that there's several articles using fractional calculus in control and signal processing.
Yes.
Any more question from
Yes,
participant?
Professor. Professor,
Yes, Kami.
Assalamu alaikum.
Waalaikumsalam.
My name is Shakil Mahmood from doing PhD in UPM in mathematics.
Yeah,
So
UPM.
would you please explain a little bit on fraction and factorial, fractional and factorial specific difference?
Sorry, I can't hear you.
I'm telling, would you please explain what is the difference between fraction and fractional, factorial difference? Difference between fraction and factorial.
But difference between fractional difference and factorial difference, you mean, yeah?
Yes, yes, yes.
Sorry, but I don't know factorial difference. Factorial, and I don't know.
Fractional factorial.
Yes, doctor. Fractional factorial.
No. I don't know, sorry. Sorry, but I can't answer this question. I don't know, really.
It's okay. It's okay, Professor.
Okay. Sorry.
Prof, I have one question from audience from YouTube.
Okay.
The question is why we need to use finite difference to do the derivation, or is there any other method to do the derivation?
Thank you. Yes, it is very difficult to solve analytically, so we should use numerical methods. There are many numerical methods to solve this kind of equations. Usually, we use finite difference because it's easy to use. But you can use not only finite difference, also other methods. For example, there is methods is there are many other methods also, but we use finite difference method, but because it's easy to use.
Okay, any other again? Is the feedback from Prof. Bekzodjon answering the question just now?
Assalamualaikum.
Waalaikumsalam, yes.
Okay, I have one question. Prof, just now from your slide, I see there is an equation of diffusion equation. May I know, and also I see from your slides, there are a few shapes of porous medium. May I know, does this shape of this porous medium involve equation? And if it involves equation, because the porous medium I can see is in the fractal forms kind. So does this equations of the porous medium embedded in the diffusion equation? May I know which equation mention the porous medium and in terms of the shape, different shape? In the diffusion equation, which equation represent the porous mediums?
Yes. Okay. I will show. Okay, I will show the slides again. And here in the first equation, this one describes diffusion in porous media, which is in the form in porous media with fractal structure. If the porous media was normal, the beta will be equal to 1. So in our case, the porous media have fractal structure, so beta is smaller than 1, but greater than 0.
Okay. The one is about derivative. For normal one, beta equals to 1, right?
Yes.
Sorry, because I have no experience using fractional derivative. But I wanted to know in details about this. And about which just now you shown us there are a few shapes of porous medium. With a small porous and bigger and bigger, and there are shapes. There are patterns. So is in this equation mentioned about that porous medium parameter?
The beta describes the porous media's you can say how it is fractured, or how this is not only porous media, it is fractured porous media. This you can see in this one.
Yes.
If the fractured channels are greater, then beta also smaller, and the diffusion is faster. Diffusion will be faster, and the distribution will be faster. If these white ones are fractures. So if they are greater, then beta is smaller and diffusion is greater. Diffusion is faster.
Or the beta indicates this fractional. This one indicates the how big the porosity.
Yes. How porous media is fractured. Yes.
Oh, okay. Thank you, Prof.
Okay.
Maybe I can open one more question on this topic. Any other
Yes.
question before we end up?
We have a question from the chat room. But
Yes.
I want to help to read that question, but actually I cannot understand what the question, what is the question is about. But let me try to rephrase. I think the question is how to study this equation theoretically, not numerically. Maybe that is the meaning of this question from I'm not sure, Miss or Mr. Kausar here.
Yeah. Yes, we can study this equation theoretically. It means that we can have this equation, the solution is only one or others, but analytical solution of this equation is very, very difficult. So for us, we are not mathematicians, we are applied mathematicians. So for us, studying the equations numerically is normal, but of course, for theoretical mathematician, it is useful to study this equation in theoretical view. There, I have read some papers in this. There are not many papers dedicated to study this kind of equations theoretically. It means uniqueness of solution, existence of solution. Yes, it is also useful.
Yes, we can also research on both area. Means for this fractional derivative, can research on the theoretical part, and also we can research on the numerical part. But mostly researchers are focusing on the numerical part.
Yes, you're right.
On the theoretical part, what we are having in theoretical part is the existing literatures on finding the solution and finding the exist solution, and also maybe finding the properties of the equation.
Yeah, you were right.
So, any other question? Yes.
Dr. Savani, Vincent here.
Yeah. Dr. Vincent, yes.
Prof, I have one question here. What are the advantages of fractional derivative compared to other models, that non-fractional derivative? Do you have any advantages, or it is better compared to existing ones?
That is my first question just now.
Doctor, it is it is useful when the normal laws are not useful. It means that they are not not adequate. They are, if the normal rules are not adequate, it means that our process is anomalous. So we should the fractional derivatives more adequately describe the process. Only in these cases it is useful and better than normal derivatives. Only for anomalous cases.
Okay, thank you, Prof. Thank you so much.
Okay, thank you, Dr. Vincent.
Sorry, Dr. Chu.
Yeah, thank you, Dr. Vincent. So with that, I think that's all. That's all for today. Thank you for all those questions. And thank you for Prof. Bekzodjon answering all those questions very well.
There is one more question in the chat room.
Okay, one more question in the chat room. Please, Dr. Nomi, please assist.
Can connect. Or all equations taken in ordinary differential equations or partial differential can convert it to fractional calculus. Yes, of course. Yes, all equations can be converted to fractional calculus, but usefulness of these equations and what are they describing, which process are they describing is another question. So, for example, we are using second order partial differential we are using, instead of second order partial differential equation, some fractional calculus for transfer in fractured porous media. So for in other cases can be used in other equations in fractional calculus. I think all equations of normal OD and PDE can be converted in fractional calculus, of course.
There's one more question. Somebody please assist the question, maybe.
What most common operators use for like Riemann-Liouville, Caputo, and others? Which one operator easy to apply it in calculation? I think Caputo formula is easier to calculate, and most of programming language is MATLAB or Python can be in MATLAB or Python we can use Caputo formula easily. So we use only Caputo formula.
Okay, thank you, Dr. Kautar, for the question. I think it almost 2 o'clock here in Malaysia time. Hopefully, everybody satisfied with the answer from Prof. Bekzodjon about fractional derivative. And thank you, Prof. Bekzodjon, for the presentation and for the Q&A. And we look forward to the next webinar in our third webinar coming soon.
Yes, yes.
I also welcome all the participants today to our next webinar that will be announced soon. And with that, thank you everyone for participating today.
Thank you all.
Is there anything you want to add on, Prof. Bekzodjon, before we leave the meeting?
No, thank you. Stay safe and healthy.
Okay, thank you, Prof. Well, we look forward to see you again.
See you. Thank you.
Okay, Assalamualaikum.
Assalamualaikum.
Waalaikumsalam.